So we're going to go ahead and take a look at the continuity and one-sided limits in this section. Basically, the informal definition of continuity is, can you draw the whole graph without ever lifting up your pencil or pen? If you actually have to lift up your pencil or pen, then it would be discontinuous at that point. Now, your definition of continuity at a point is the following. All three of these have to be true for it to exist, to be continuous at a certain point. The first part is saying your function is actually defined at that point. You don't necessarily know what it is right now, but you can actually take your value of c that you're wondering about your continuity at and plug it in for your x and get a certain value out. And the second part is saying your limit as you approach x being c does exist. The third part saying, well, the first two things have to be equal to each other. Sometimes your function can exist, sometimes your limit can exist, but they're not equal to each other. So then it would fail the bottom one. If any one of these three parts fails, or more than one part fails, it is not continuous, and we would then say it is discontinuous at that value of c. So when we're talking about something being discontinuous, it's typically one of these situations. There's another situation that it could be also. We could basically have a hole or a gap in your graph. Sometimes that's referred to as removable discontinuity. Sometimes you could come in from one side and then you'd have to jump up to be able to get to the other side. That's referred to as a jump. And it's not continuous because your limit does not exist, because it's approaching one value on the right, approaching another value on the left. Here it's not continuous because the value of c does not exist. Here, as you approach from the right, approach from the left, you're approaching the same height, so your limit exists. And when you plug in the value of c, you get out this value down here. But because the y value of what it's defined to be does not equal the limit of what it is not continuous. Now, discontinuities are often infinite discontinuities, which are vertical asymptotes, which we didn't talk about up here, or a finite jump, that would be like the center one, or a removable discontinuity, which is like this upper left one. So as we look at this first function here, f of x is equal to 1 over x, we would say it's going to always be continuous except what would cause the bottom to be 0. Well, what would cause the bottom to be 0 would be 0. So it's always going to be continuous except what causes the bottom to be 0 at 0. And in this case, it would be a non-removable, and it would be the infinite discontinuity one when x is 0, because that's where you have vertical asymptotes. Looking at this one here, we would say it's going to be continuous except what would cause the bottom to be 0. In that case, that is 1. Now, for this particular problem, we would say it would be a removable discontinuity, because we could figure out a certain value at 1 and make it a piecewise function and say, well, it's always going to be this except 1, and then when it is 1, it's going to then be, say, 2, and it will be a continuous function. We could do that by going ahead and looking at the top of this and saying, oh, that's an x plus 1, x minus 1. Simplify that down. Your x minus 1's top and bottom would cancel down. It would leave you with an x plus 1. And then plug in 1 for x, and that's where the 2 would come from. When we're looking at this one here, we're wondering, well, let's see. This is a line. We know a line is always continuous. And this is a parabola. We know a parabola is always continuous. The question is, does our parabola meet up with your line when x is 0? So one way you could do that is see if your limit as x approaches 0 is the same. Well, if you take 0, plug it into the top one for your left-handed limit, you would get 2. If you take 0, plug it in, or not 2, if you plug in 0, you get 1. If you take 0 for your right-handed limit and plug it in here, you would also get 1. Since you get 1 on both sides, your limit would exist and it would be continuous. Your sine function, you should remember, you can basically draw it without ever lifting up your pencil. There's no vertical asymptotes, no holes, so it would be continuous. Now looking at the graphs, you can see this is your sine function. It's going to be continuous. Here, this was that line in parabola 1. You can see that they meet up, so yes, it would be continuous. This one here has a hole in your graph, and you can see that it would be referred to as a hole removable discontinuity. This one here, the first one we looked at, has a vertical asymptote here, so it has a non-removable infinite discontinuity is what that one's referred to as. Couple of things we have. If there is no plus or minus sign after your a value, then that's referred to as a two-sided limit. And that's what you'll notice right here with this one. But if there's a little plus as an exponent, that means you're only looking at your limit, the right-handed limit. You're looking at values that are slightly greater than that, just to the right of that. And then we have your left-handed limit if you have a little bit of a negative sign. So just to the left of that value of a, what is your output approaching? So if we look at this graph right here, which is the absolute value of x over x plus 2. So you can see to the right of your y-axis, which is x being 0, you're always at a height of 3. To the left of your x-axis, which is x equals 0, you're always at a height of 1. So we would say your right-handed limit, when you come in just to the right of 0, you're at a height of 3. So that's your limit there. Your left-handed limit, just to the left of 1, as you come in here, just to the left of, or not just to the left 1, just to the left of 0, sorry about that, you can see that you're always at a height of 1. So your left-handed limit is 1, your right-handed limit is 3. We would say your two-sided limit does not exist because these two values are different. The only way your two-sided limit exists is both your left and your right-handed limits are equal. So as we look here, if your right-handed limit is equal to L and your left-handed limit is L, basically your left and your right limits both equal the same thing, then your two-sided limit does exist. That's what this is saying. This is basically saying if you're looking at continuity from one side or the other side, basically it's just taking the 3 steps of continuity and using your one-sided limit. It's not that big of a deal. Don't be overly concerned about it. We're not going to really be dealing a whole lot with that. And here it's saying if you have two functions that are continuous, if you multiply them or add them, or multiply it by another number or divide them, they're going to be continuous except if you're dividing if the bottom is ever equal to 0. It's saying polynomials are always continuous. Remember, a polynomial, your exponents have to be positive whole numbers. It's saying rational functions are continuous except when the bottom is 0. Radical functions are continuous, assuming that if it's an even root, what's inside is not negative. Your trig functions are always continuous except what causes them to be undefined, like where you have vertical asymptotes and things like that. We also have the intermediate value theorem. So suppose you have a closed interval. And you plug in your A value, you get out a certain Y value. You plug in your B value, you get out a certain B value. And these are at different heights. Your intermediate value theorem says that to go from the height of this one here to the height of this one here, it's going to take on all the values in between these two heights at some point in between the input of A and input of B. That's really what it's saying. So what are the consequences of this? Well, it has to be a continuous function. The consequences is it allows you to be able to say something does exist. Often when we were looking in pre-calc, we were saying, well, there has to be a zero here because at this value of x, you're above the x-axis. At this value of x, you're below the x-axis. So therefore, it has to cross and have the x-axis and have a zero at some point in between A and B. So this one here, they're wondering, can we use the intermediate value theorem? Yes or no? Well, it has to be a continuous function. We know that this is continuous because that's a line. We know that x minus 1 is continuous because that is a line. The question is, do these two lines meet up with each other when x is 1? Well, if I take 1 and plug it into the top one, I get out 2. If I would take 1 and plug it into the bottom one, I'd get out 0. So these two lines don't meet up. They're not coming in at the same height, so it's not continuous. So therefore, you cannot use the intermediate value theorem. So consequently, what can we do with the intermediate value theorem? So suppose we wanted to show that we had a 0 between 0 and 1 of this function. A 0 meaning you're crossing the x-axis. The y value is 0. Well, we know this is a polynomial, so we know all polynomials are continuous. So we would know it would be continuous, so we can move forward with trying to use the intermediate value theorem. So let's take these two endpoints of our interval and plug them in. Plug in 0 to your function. Well, if you plug in 0 for your x's, in this case, you would get out -1. Then we're going to take and plug in, whoops, our 1 right here to our function. Plug in 1, and in this case, we would get out 2. Well, that's kind of nice because we can see that when we plug in this, we get out this. In other words, we get this point. And then when we plug in 1, we get out 2. In other words, we get this point, 1 comma 2. Oh, we know it's continuous. We know in the green, we're below the axis. We know in the blue, we're above the x-axis. So it's continuous, so we have to go from the green to the blue without ever lifting up your pen. So at some point, we have to cross in between our 0 and our 1. We don't necessarily know where we are crossing here, but we know we have to cross somewhere in between 0 and 1. That's what this intermediate value theorem is saying. So basically, since you're below at 0, you're above at 1, it's got to cross somewhere in between and have a y value being 0. That's the intermediate value theorem. And we have a polar bear in a blizzard.